Hello, this is the second part of the chapter 5.5, and we will talk about complex eigenvalues. So in general, we should get the complex eigenvalues, especially for the large matrix, because if we have n by n matrix, we know that the eigenvalues is a solution of a characteristic equation. And if we have n rows and n columns, and we are multiplying diagonal element of by finding determinants, we should have a polynomial of degree n's. And polynomial of degree n's, we always have n roots, and those roots can be equally likely to be our real or imaginary one. So we will, in the real world, when we take a large matrix, we should get rather large number of imaginary eigenvalues. How do we get to deal with them? Because so far we were mostly working with the real numbers because we are enjoying working with Rn and writes everything in terms of Rn. It seems like that's not the case anymore. It seems like we need to actually expand our vector space from Rn to Cn to be able to include the imaginary eigenvalues and imaginary eigenvectors. Okay, so now when we are including Cn in our vector space, we can easily solve the characteristic equations for any matrix. And we say that if scalar or number a minus lambda I is satisfied equation a minus lambda I is equal 0, if and only if there is a non-zero vector x in Cn, the complex number vector space, such that product of matrix by x is equal lambda x. So we have exactly the same definition as it has before, but now our lambdas and x's can be actually complex. So we refer to lambda as a complex eigenvalue and to x as a complex eigenvectors. And we know from the previous part that they actually complex eigenvalues and eigenvectors come in the complex conjugate couples. Okay, let's try to see how do we work with the complex eigenvalues and eigenvectors. And again, it's very similar with the real one, with a couple of small details which I will point out. Okay, let's take a matrix, rather simple one, 3 by 2 matrix, and try to find its eigenvalues and eigenvector. So we start by writing down characteristic equations and set its determinant equals 0. So we will get a characteristic polynomial, lambda squared plus 1 is equal 0. So our lambdas will be the positive and negative square root of minus I. And the square root of minus 1, we are calling an I. So in both positive and negative I, when we square it, should give us 1. Okay, great. So now we have two eigenvalues, and indeed they are complex conjugate of each other, plus I, negative I. So imaginary parts have a different sign. So let's try to find the eigenvectors. So for the first eigenvalue, lambda 1 is equal I, we will write a homogeneous equations by subtracting our eigenvalue I times the identity matrix from our matrix A. And that's our equation which we need to solve to find the vector x, which is an eigenvector. And normally what we would do here, if we had a real eigenvalues, we would form the augmented matrix and reduce it to the echelon form. Unfortunately, when we deal with the complex numbers, the reduction of the matrix to the echelon form can be quite messy. So when we're dealing with complex eigenvalues, it is much easier just write system of equation. So we will write our matrix A minus I times I, and just put the two components of our vector x and x1 and x2 and set it equal 0. and then just expand it in the two equations. The first row multiplied by the vector x1, x2 should give us the first equation, and second row multiplied by vector x1, x2 should give us a second equation. But the positive thing is, similarly to the real eigenvalues case, our equation usually has a free variables, which means that our equations are reduced to pretty much the similar one. So for example, here, the first one, when we simplify it, give us x1 is equal ix2, and the second one will give us exactly the same equation. So we still have a free variable x2, which we are free to choose whichever makes the easier or pleasantly looking vector, eigenvector. So I'll choose x2 is equal 1 here to get the eigenvector. I'll call it v1, which will be just the first component will be I, and the second one will be 1. Okay, that was the first eigenvector. Let's try the second one by taking our complex conjugate eigenvalue lambda 2 equal -1, and again writing down our system of equation. And again, we have a free variable here, so we don't even bother writing the second equation. The one will suffice. So x1 is equal minus ix2 is our equation, and x2 is a free variable. So again, I'll choose as equal 1, and our second vector will be minus I1. And again, the complex conjugate of each other. Okay, we did a good job here. We find eigenvalues and eigenvector, but it probably doesn't feel very satisfactory. In the real eigenvalue case, we always knew that our eigenvalue just will subtract or shrink our eigenvector. It's less straightforward in a complex case. So let's just try to think, what does this transformation mean? What kind of ideas our eigenvectors and eigenvalue represent? Okay, let's look back at our matrix, and we know that each matrix represents a linear transformation. So let's see what kind of transformation our matrix with the complex eigenvalues and eigenvalue represent. Okay, and just to make it easier, just look at this pictures of fish, and we will try to see what's happened to it when we apply the linear transformation described by our matrix. Okay, we know that for linear transformation, to figure out what's happened after the transformation, all we need to do is figure out what's happened with our unit vectors, E1 and E2. Okay, when we take our vector E1 and apply our transformation, it's transformed into the point, it's moved into the point 1, 0 right here. So basically the tail, our fish will go where the head is, in this corner. Okay, so let's look at the second one. So our second vector, 0, 1, now transform into the second column of our matrix A, which -1, 0. So our second component will go somewhere on the left part of the x-axis. So what we have is the fish like this, or in other words, it's rotated by pi/2. And that's an interesting case. So what if we continue? Again, we can rotate fish another pi/2 and another time, and eventually, after several rounds of this transformation, we end up with the picture we started. And here, because we're rotating by pi/2, we only need 4 rounds of transformation to return to our original image. And that's one of the most wonderful things about the complex eigenvalues. They are usually represent the transformation which have a certain repeatability in it. So the one which move along the what we call closed trajectory. So if you apply this transformation again and again, your point will move in some kind of closed loop or periodically repeat. So complex eigenvalues are excellent to represent the repeatable process. And in the next part of the series, we will look more on the more complicated cases of the complex eigenvalues.